Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really fascinating area, neurosymbolic decision trees.
Neurosymbolic decision trees, yeah, it sounds like a mouthful, but the core idea is to combine the strengths of neural networks with the more traditional, rule-based approaches of symbolic AI.
Exactly. Think of it as trying to get the pattern recognition capabilities of deep learning to play nicely with the logical reasoning of symbolic systems. So instead of just throwing data at a neural network and hoping it learns something, you're giving it some structured knowledge to work with.
And that structure is key. I mean, deep learning is great at finding correlations, but it doesn't really understand anything. It just sees patterns. Neurosymbolic systems are trying to encode some actual understanding, even if it's a simplified version.
What's really grabbed my attention is how closely this approach aligns with what we understand about the brain. We don't just process information statistically. We also use logic, reasoning, and prior knowledge to make decisions. Neurosymbolic models are attempting to mimic this hybrid approach.
Right. You could say that it's trying to capture the best of both worlds. The ability to learn complex patterns from data, which neural networks excel at, and the ability to do logical deduction and reasoning, which symbolic AI is better suited for. I think that's really the sweet spot we need to hit for real AGI.
I'm still skeptical that deep learning is the answer, even in a hybrid approach. But I do agree that combining it with symbolic reasoning is a step in the right direction. We need to move away from these black box models where we have no idea why they're making the decisions they are.
Yeah, the explainability is a huge issue. With traditional decision trees, you can trace the path a decision took and understand why it made that choice. Deep learning. Good luck with that. It's just a bunch of weights and biases. But what I see with neurosymbolic systems, the real trick is, how can you make the most efficient translations between different coordinate representations? That's what I am most concerned with in the current research.
So, let's break this down a bit. What exactly is a neurosymbolic decision tree? It's basically a decision tree where the nodes can be either symbolic, representing rules and logic, or neural, using neural networks to make decisions based on learned patterns.
Exactly. So at each node in the tree, you might have a neural network that's been trained to classify images, for instance, and then, based on that classification, the tree branches off to different subtrees, each representing a different logical rule. The trick is making the handoff between neural and symbolic components seamless and efficient.
And this is where the challenge lies, right? How do you translate the output of a neural network, which is often a probability distribution, into a symbolic representation that can be used for logical reasoning? It's not always a straightforward process.
That's a crucial point, and it gets even more complex when you consider spatiotemporal data. How do you represent relationships between objects in space and time in a way that both neural networks and symbolic systems can understand? I keep thinking about how humans effortlessly translate between different coordinate systems, like when we catch a ball. We're constantly transforming visual information into motor commands, and it all happens seamlessly. How do we replicate that in a machine?
That's a great example. Think of a self-driving car. The neural networks are fantastic at image recognition, identifying pedestrians, traffic lights, other cars. But then, the car needs to make decisions based on that information. Should I brake? Should I change lanes? That's where the symbolic reasoning comes in. It needs to apply rules and logic to the sensory input to navigate safely.
Yes, and imagine a medical diagnosis system. The neural network can analyze medical images, like X-rays or MRIs, to detect anomalies. But then, a symbolic system can take that information, combine it with patient history and medical knowledge, and make a diagnosis based on established medical guidelines. It could even explain the reasoning behind the diagnosis, which is something a pure deep learning system can't do.
That explainability piece is huge, not just for medicine, but for any application where trust and accountability are important. You can't just have AI systems making decisions that affect people's lives without being able to justify those decisions. And I think neurosymbolic approaches offer a way to build more transparent and trustworthy AI.
But even with the explainability, you still have that underlying question of how well it can generalize. Can it apply these rules and logic to situations it hasn't seen before? That's where I keep coming back to the importance of spatiotemporal reasoning. If the system can understand the relationships between objects and events in a more fundamental way, it should be able to generalize better.
So, what are some of the techniques being used to build these neurosymbolic decision trees? One approach is to use something called knowledge graph embedding.
Right. Knowledge graphs are essentially structured databases that represent relationships between different entities. So, you might have a knowledge graph that describes relationships between diseases, symptoms, and treatments. And then, You can use neural networks to embed these entities and relationships into a vector space, which allows you to perform reasoning and inference. The neural network can essentially learn the structure of the knowledge graph.
That's a good way to inject some prior knowledge into the system. Instead of starting from scratch, the neural network has a pre-existing knowledge base to work with. But again, it comes down to how effectively you can translate between the neural representation and the symbolic representation. Are you losing information in the translation?
And how are you representing the spatial and temporal relationships within that knowledge graph? Are you just treating them as static facts? Or are you capturing the dynamic nature of the world? Can the system reason about how objects move and interact over time? That's what I'm really interested in.
Another approach is to use something called differentiable reasoning.
Differentiable reasoning is cool. It's about making symbolic operations like logical AND, OR, and NOT differentiable so that you can train them using gradient descent, just like you train neural networks. This allows you to learn the rules of logic from data rather than having to hand code them.
That's interesting. So instead of explicitly defining the rules, you're letting the system learn them from examples. But does that really give you the same level of control and understanding as a hand-coded rule? I worry that you might end up with rules that are hard to interpret or that don't generalize well.
And how does this differentiable reasoning handle changes in perspective or coordinate systems? If you learn a rule in one context, will it still apply in another context? I suspect you'd need some way to explicitly represent the transformations between those contexts.
There's also the approach of using spiking neural networks in combination with symbolic systems.
Spiking neural networks. I'm intrigued by those. These are more biologically realistic models of neurons that communicate using spikes or discrete pulses of electricity. The timing of these spikes can carry information, which allows for more complex computations. It's a lot closer to what the brain actually does.
Potentially more energy efficient too, right? Because the neurons only fire when they need to. But are they really necessary for building intelligent machines? I'm not convinced that we need to perfectly replicate the brain to achieve intelligence. Maybe a simpler, more abstract model is sufficient.
But if you're trying to model spatiotemporal reasoning, the timing of spikes could be crucial. It could be a way to encode information about when events occur and how they relate to each other. The problem then becomes how you translate this spiking activity into a symbolic representation that can be used for reasoning.
It seems like the key challenge is finding the right level of abstraction. You want to capture the essential features of the brain without getting bogged down in unnecessary details. So, what are some of the limitations of these neurosymbolic decision trees?
Well, one limitation is the scalability. As the complexity of the problem increases, the size of the decision tree can grow exponentially. This can make it difficult to train and deploy these systems in real-world applications. Although, if we just keep getting more data and building the models more robustly, I suspect this can become less of an issue as processing power increases.
And another limitation is the brittleness. If the rules in the decision tree are too rigid, the system may not be able to handle unexpected situations. You need to find a way to make the system more flexible and adaptable.
And I keep coming back to the issue of spatiotemporal reasoning. If the system doesn't have a good way to represent and reason about space and time, it's going to struggle with any task that involves understanding the physical world. This is so crucial and usually an afterthought in the models I have been analyzing.
So, where do we go from here? What are some promising directions for future research in this area?
I think we need to explore new ways to integrate neural networks and symbolic systems more seamlessly. Maybe we can develop new architectures that allow for bidirectional communication between the two components. Or maybe we can find ways to train neural networks to directly generate symbolic representations.
I think we need to focus on developing more robust and explainable symbolic representations. Instead of relying on black box neural networks, we should be building systems that are based on clear, well-defined rules and logic. This will make it easier to understand and trust the decisions that these systems make.
For me, the most promising direction is to develop new ways to represent and reason about space and time. We need to build systems that can understand the relationships between objects and events in a way that's both flexible and efficient. I think that's the key to unlocking true general intelligence, especially for complex chaining operations.
From my perspective, I'm particularly interested in exploring how we can incorporate neurobiological models of cognition into neurosymbolic systems. How can we leverage our understanding of the brain to build more intelligent machines? The concept of a global workspace, a mechanism for routing information and enabling chaining of operations, is especially intriguing to me.
That's a great point. The global workspace is definitely a key concept. If routing information is critical for chaining operations, Then how does the size and complexity of the global workspace relate to the ability to chain longer and more complex sequences? A larger, more interconnected workspace should support more sophisticated chaining.
But again, how do you ensure that the routing of information within this global workspace is not just a series of noisy, non-deterministic connections? A well-defined, rule-based system could be the key to understanding and controlling these operations.
And how does this global workspace handle different coordinate systems? How does it translate between the visual representation of an object and the motor commands needed to interact with it? I think that's a crucial question.
Exactly. It all comes back to the idea of translation. How can we build systems that can seamlessly translate between different representations of knowledge, whether they're neural, symbolic, spatial, or temporal? That's the challenge that lies ahead.
It also raises the question of how we can quantify the effectiveness of this global workspace. Are there metrics that can be used to measure the capacity for different types of information integration in a global workspace, similar to measuring network capacity?
And how do we prevent this global workspace from becoming a bottleneck? If all information has to be routed through this central hub, it could limit the system's overall performance.
That's why I think the hierarchical aspect is so important. A truly spatiotemporal global workspace would need to incorporate some form of hierarchical reasoning, building upon previous steps and contexts.
Right. So, to summarize, neurosymbolic decision trees offer a promising approach to building more intelligent machines by combining the strengths of neural networks and symbolic systems. But there are still many challenges to overcome, including scalability, brittleness, explainability, and the representation of space and time. Future research should focus on developing new architectures, more robust symbolic representations, and better ways to model spatiotemporal reasoning and even incorporate neurobiological models. I think all of that is very important for all of this.
Yeah, I am excited about the possibility of incorporating hierarchical temporal memory, HTM-like structures into deep learning models. It seems like those models might offer a more biologically plausible framework for understanding how the brain performs tasks that involve sequential reasoning and memory. I feel like we could take a big step with this.
I'm eager to see more research into how we can build systems that can not only reason about the world, but also explain their reasoning in a way that humans can understand. That's essential for building trust and accountability.
And I'm going to keep pushing for more research into spatiotemporal reasoning. I believe that's the key to unlocking true general intelligence and enabling machines to truly understand the world around them.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion informative and thought-provoking. Until next time.